Okay. Assalamualaikum warahmatullahi wabarakatuh and very good evening. Before we begin our session, let we recite Ummul Kitab, Surah Al-Fatihah for blessing and ease for our program, Al-Fatihah. Amin, amin, ya rabbal alamin. Ladies and gentlemen, distinguished colleges and dear students, it's my great pleasure to introduce our visiting lecturer for this session, IR Azizul Afandi bin Azizul Akmal. IR Azizul is a senior bridge engineer with over 14 years of professional experience in structural in bridge engineering. He is currently serving with Asia Infrastructure Solutions and has previously held as a senior and principal engineer position in both Malaysia and also Singapore. He is a professional engineer registered with Board of Engineer Malaysia and also Asian Chartered Professional Engineer with extensive experiences in the design and independent checking of major bridges and rail infrastructure projects, include MRT, LRT, and international rail development in Southeast Asia. In addition, he also had experience in design for industrial and residential buildings. This evening, IR Azizul will be sharing his professional insight through a lecture entitled Structural Design Moving from Theory to Reality. Without further ado, it's my honor to invite IR Azizul Afandi to deliver his lecture. Please, IR Azizul, to share your slide.
All right, thank you very much, Dr. Mazlan. Okay, first, how I'm going to share the slide. Share screen. Okay. So I guess you can see my slide, right?
Yeah, I can see clearly.
Okay, Alhamdulillah. Alhamdulillah Rabbil Alamin wassalatu wassalamu ala asyrafil anbiya'i wal mursalin sayyidina Muhammadin wa ala alihi washabihi ajma'in. Amma ba'd. Alhamdulillah, first of all, I would like to thank Dr. Mazlan for the invitation for today's special lecture, and also to the University University Malaysia Perlis Unimac for this invitation. So actually, this is the first time that I will be giving lectures. Anyway, I hope that these sessions will benefit to all the students. Yeah. Okay, without further ado, so as a brief, I think since Dr. Mazlan already briefed about myself, so I think I'm not going to touch more on the my background. So anyway, let's straight to the lectures. Okay. So basically, back in the during in your the left hand side is actually what you learn in the classroom, but once you graduated afterwards, then you will be facing a lot of things. For example, on the heavier structures that is you can see in the right hand side. So my goal today is actually there's a to bridge these gaps between the two for whatever that you learn in classroom and how you apply in the real life, in the real engineering career. So but there's some of the dilemma when you start the work. First of all is you will be overwhelmed by the software. So you could some new students or fresh graduates might have been trapped in the software. We call it software traps. And also there will be a real world constraint. and also we start with the how to apply the engineering intuitions. So so today we're going to go through around four basic titles, which is the first one. We are going to talk about the design flow of the from the how we're going to do the a typical bridge design from the blank page to the buildable drawings. But actually, this I'm not going to go through the design parts. It's just that I'm going to explain to you the flow of the works in overall. Then the second one, we will go through the one of the case study that I prepared for today, which is there's one of my previous jobs, which is the rail track slab design. I think it is actually a simple structure, but it's quite interesting, I think. So later on we can see. Then the third one, it will be the sanity check, where how we going to find how we going to ensure that our model is correct, everything. Then the last one is the rule of thumb for the engineer. I will touch a bit on that lah. So we go through the straight away go to the first topic. So the topic is a bridge design flow. Okay. I'm not sure whether your class, meaning your course is have a bridge design modules. For myself, previously I learned the bridge during my masters. During the degree, I'm not exposed to the bridge design concept. Basically, the bridge design is quite different compared to the typical buildings design. So in general, so the first thing that when there's a project, so the first thing is that we need to plan. So the first thing comes is when we need to have the plan, and what is going to do. Then after that, we're going to get the profile, because this is the bridge. Usually bridge will serve the either roads or rails usually. So it's either coming from the road engineer or rail engineer or alignment engineer. It depends on the type of the projects. So then the alignment engineer usually will provide the profile, the design, the profile, and then the sections of the road or structures, the road or the rail, what the width, what's the one, for example, the road, how wide the road, is it the typical R2 JKR roads, or is it highway? So that is coming from the alignment engineer. And then from that, after that, then only we proceed with the modeling. So this modeling, we are talking about the beam modeling. It's not design modeling yet. So the beam modeling is to generate the drawings, and also to link to the analysis. So this beam is quite new in the market, especially in Malaysia. Previously, we use the old method, which is we just use a CAD, and then straight away do the come up with the drawing from the CAD. But now the beam is coming more popular. So so my design flow is centralized based on the beam. So then when we start pre-modeling the beam model, we modeling the bridge. We just put in the size, the beam. For example, if it is a balance cantilever box girder bridge, we put in the girder size first. It's a predetermined. It's not the final design yet, so we put in some size, and then the column we just place it at the location that we think is suitable based on the judgment. And then only after that, if everything is in place and it's agreed by the preliminary agreed by the client, everything, then only we start to do the structural modeling to check whether the structure, the size is correct, everything, and we have to come up with the details. So this come to the bridge structure modeling and analysis. And at the same time, it can go concurrently. The modeler will generate the drawings. So the drawing sometimes can be either from scratch, or the engineer will give the prelim expectation size. For example, if the beam of the bridge size, if the engineer know already the span of the bridge, so sometimes he can predetermine what's the depth of the beam, how many numbers of the beam that he need. So he will straight away give the drafter to start to do the design concurrently, instead of waiting for the completeness of the to complete the modeling and the analysis design. So this process goes concurrently. Okay, so before the engineer starts the modeling and analysis, of course, we need to gather up the informations, like what's the load input that we're going to put in our models, what's the load combinations, the information from other parties, like from geotechnical parties, to get their informations of the soil modulus, and also the soil springs, for us to model in our software. So all these have to be based on the any related or relevant codes or code practice. For example, in Malaysia, we are now moving to the Euro codes, or sometimes we still using BS code. So depends. Back in Singapore is already full using Euro codes, and even Singapore have their own full Singapore annex already. For Malaysia, sometimes some of the codes, I think, still don't have the Malaysia annex, especially for bridge. I think it's still following the UK annex. So from the codes, everything we determine what's the loads. For example, for the bridge, how we determine the wind loadings, the temperature loadings, the traffic loadings, everything is from the codes. And then also, this is my personal suggestion, that before we start any model, we should have an initial column load taking. Initial column load taking means that we based on our desk study, we try to calculate what's the loading that goes to the columns and then transfer down. So then we can have like predetermine what's the final column force at each column. Or maybe we can do, or like if you have buildings, then it can be 1 or 2 columns. If so for beach, we determine by one, maybe the longest at the longest span, and one at the end span. So later on, I will explain why we need to have this initial column load takings. Okay, and then after we do the modeling, and then we do and put in all the loads inputs, everything, then we run the analysis, and then after we found the errors, then we do some debugging. Then after we satisfied with the analysis, then we extract the forces and the stress for our next steps. So the first step, usually we will get the pile working loads first. So for the pile working loads, usually we are going to give to the pile working loads to the geotech engineer. The geotech engineer will from the working loads that we give to them, they will start their AGPC, which is the analysis of their geotechnical pile capacity, and also they will determine what the type of pile that is suitable for our structure, whether it's a bore piles or span piles. It depends on the soil conditions. that they encounter. Then from their analysis. Then they will check the design. So if the design is okay, then we can proceed with the pile and the pile cap designs. So if for example, the pile working load is too big for the current proposed pile size, then maybe we have to turn back, and then we have to turn back to the modeling, then maybe they change the size as required. Then the process come again. We update the modeling again, everything, and then we go until it's okay. And then after that, the forces that we get from our analysis, we will start to do the element designs. Element design means that all the RC designs, the structures, the pier, crossheads, and abutments, and also the main superstructure is either pre-stressed concrete beam or precast beam. It depends on the type of structure that we propose. So it can be a segment, either segmental or beams. And then we do the slab design on top of our superstructure, and also some miscellaneous structures, such as miscellaneous elements. It's like bearings or parapets. So we have to do the design as well. So, but the core elements is the key element is these five lah: the pier, crosshead, abutment, slabs, and also the beams. After all this design, we check if the design is, we found that it's failed. For example, the pier design cannot work. The current size, although it's like our proposed like 1.5 meter diameter circular columns, still cannot work. So what should we do? So we have to determine whether we need to update to change the size, or just the rebar, we have to increase the rebar. So it depends. If we have to change the size, then we come back to the beam model. It's always the looping process until it's finished. So we do then we come back to the beam, then the beam will updates, and again we import everything again in the analysis, and then we do one more time the process until it's okay. So if there's no change that required, or it still fail, that's not when we do the analysis. For example, the beam is failing, so if what we determine, we check, we don't need to change the size, meaning we don't have to change the our general arrangement. So what we did, we maybe we need to increase the reinforcements, for example. So then we don't need to go to the beam to the modeler. We just need to change we have to determine whether we need to update the model, our structure model, or not. If no need to change structure model, we just change in our structural design. Then okay, we straight away go to the element design again. This process is again looping until it's fine. Or if we need to change the structure model, then so we go back to our modeling, and then again we change everything. Then the same process come again until everything is fine. Okay, then if everything is okay, so we have to determine whether we need to do optimization or not. What is optimization actually? So I think optimization, I seldom hear the term during my study last time. But when we come to the industry, then we will always hear this terminology, optimization. Usually the client will love this terminology because of what? Because it's optimization means that we design it close to the limit, meaning that we are design it to optimize, meaning that it is very economical design. So client will like it. So if we need to do the optimization, meaning that our prelim size, for example, our prelim crosshead is too thick or too the width, then we still based after our analysis, we found that the utilization ratio is just like maybe 0.6. So we have like around 40% buffer. Definitely we have to justify to the client why we design to that. So in that case, then we have to do optimizations. So we have come back to our modeling, then we reduce the size, for example, or increase the rebar, and then do one more time until it's optimized. If you don't need more optimization, then we finish the whole process already. So the design calculation, we can come up with the design calculation report, and at the same time, the beam model previously is going to produce the drawings that we required, all the cut sections of the beam details, the columns reinforcement details, whatsoever. So that's about it for the design flow of the bridge in general. And also actually it's not specific to the bridge. Actually this flow also almost similar to any kind of structures. It's just that maybe the elements is different. Okay, so far you have any question, I think you can just jump in or maybe text. The Dr. Mazlan help to, if there's a question from the floor, you just raise up so that
All right,
I
yes,
can
I
stop
will.
anytime. Yeah. Okay, so I think I'll continue. So we go to the uncommon case that I said just now. We are going to see the the how the track slab design. I choose this because I find it quite interesting because it seems like a simple structure, just a slab sitting on the bridge. So in this case, the track slab is actually is, we call it is a ballastless. You know, ballast is actually the gravel, the gravel stones that you usually see at the tracks, the train tracks, right? So in this case, without the ballast, there's a concrete slabs. So as shown on at the right side is the typical form of the track slabs. So there will be a track slab, and then they have like a derailment upstand there. Can you see my pointer? I just wondering when I'm
Okay.
moving.
Moving.
Yes. Okay. Okay, thanks.
Moving.
Okay. Then okay. Then after that, on top of the track slab, there will be a rail. So the rail will be sitting, and then it will be fixed by the fastener. We call it this a fastener. Is will be at a certain intervals. Sometimes it can be 600 mm spacing, or even more than 600. Okay, and then usually the track slab will be will be anchored or to the main deck lah. So this is the main deck. Usually they will have some form of the shear studs. Okay, we go straight to the this is the geometry of one of the track slabs that I've designed before. So this is actually what I done for the Palembang project, Indonesia. So they have a bridge there. It's an existing bridge, but then they wait for sometimes maybe 1 or 2 years. After that, only they're going to install the track slabs. So then they appointed us as one of the as a consultants for the track works designs. So so in this case, the track slab will be cast in situ concrete. So sometimes the track slab can be a precast as well. It depends on the preference of the clients. Okay, this is what I've said just now. You call fastener or direct fixation fastener. We call it DFF. So it's fastened to the track with anchorage. So how are we going to design this track slab? Because it's slab, but it's sitting on another slabs. and then also it's exposed to the weather. So first we are in this case we are going to use the strut and tie method to design the main reinforcement. So the main reinforcement will be a transverse reinforcement. It's a main reinforcement. Then the reinforcement is along the track. So in this case, you can see the what I draw here. The interesting is that we try to determine how we're going to do the strut and tie method. So in this case, because this is a canted track, canted means that the track is like not straight. It's like having some sort of like elevation. So if in on the for the road design, we call it elevation, super E, right? Super elevation. But for the track, we call it cant, C-A-N-T, canted. So in this case, with the canted, so the track is not straight lah. So there's some degree on it. So what we're going to do is we base on the force, vertical force from the track, then we are going to distribute by certain degree, and then we form of the strut and tie method. So the tying part is the bottom part, is where we put the main reinforcement. So the distribution is to the certain degree. How we determine this? This one we predetermine we measure it in the CAD. So we assume that the distribution is like 45 degree. So it's 45 degree to the down there, and then it's straight. When we mark up there, then we make some for conservative design, we take it half of the dispersal. So the actual dispersal is this width, but we didn't design it to this width. If we design it to this width, it's going to be very low reinforcement and very low bending moments. So to make it more conservative, so we take it half of the distribution. So half of it, then we found we find the degree, and then we can calculate the strut and tie. So this is how we calculate the strut and tie method. So we got the force. The force is from the codes lah. Usually the codes will determine what's the force. So in this case, 146 kilonewton per meter is the already times the ultimate factor. So with the degree of 60.6, so we recalculate using the trigonometry, and then we get the tension force at the bottom of the slab. From there, we compare. So we get the stress, and then from there we determine what's the capacity. So in this case, we put in the reinforcement is a 10 mm diameter with a 300 spacing, and then we calculate, and then we found that the design is satisfied. So the tensile capacity is the force is less than the tensile capacity, so the design can works. And then other than that, what else we have to check other than the strut and tie from the direct from the force is the next that we are checking is the differential temperature effect. So here, as you can see, this is the typical behavior of the slab when it's exposed to weather. So okay, I have a short quiz here now. So maybe you can if you can just answer in the it's a very simple question. You can answer like A or B, or maybe Dr. Mazlan can do a quick poll that so that they can give the answer, and we want to see just for the engagement. Okay, see, if you look at carefully this diagram, do you think the diagram is correct?
Okay, guys, you can type A or B in the chat room, in the chat, please. So
In the
we
chat.
can who try to answer that.
Okay, let me try.
Try to answer that in the chat room.
In call message. How to? I can type the POL.
So which one is the correct one, right? A or B?
Is no, the question is this diagram correct or not?
All right. Okay. Okay.
Ah,
Sorry.
you have to look carefully whether the diagram is correct or not. Is look like yeah, you see first. Just go around 30 seconds. But how to do the pull, doctor?
Pool. I'm not sure have pool in
Oh,
here,
you
but
haven't done before lah. Never mind lah, never mind.
uh,
Okay.
try to answer in the chat.
Yeah,
Because
everyone can try to answer in the chat. So
so at the same time we can take your attendance. Try to answer
yeah,
that.
correct, correct. So
If you want your
uh,
attendance taking, so please answer that.
you see, when for example A and B, why I ask whether the diagram is correct or not? If you have to carefully look at the stress. Is it correct that for example at the top diagram, the compressive stress at the top, and then the tensile stress at the bottom? While the other diagram, the tensile stress at the top, but the compressive stress is at the bottom. Is it correct or not? Is something is to me it looks like weird, right? Yeah,
Yeah, it's
yeah.
like
We give like
weird
yeah.
to me too because it's a
Ah,
temperature effect, right?
yes,
Quite
yes, yes. That's right.
because I myself confusing.
Ah, yeah, correct. So that's why. So that's why I asked. All right, good. Some of it say B. Looks like major say not correct, right? Okay, we give like maybe 10 more seconds. Okay. Uh,
Try to answer so I can take your attendance. Most look like B,
okay. Mostly say the is not right, right?
Yes.
Okay. Actually, okay, I give the answer lah. So actually the answer is a correct diagram. This diagram is actually is you can get it like in the journal, everything. The diagram is correct
Mm-hmm.
because what this is a differential temperature effect. So uh, it's because of the the effect. I think I explain later because I think there's another question. So okay, questions two. So we know that this diagram is at the day and also at the night. So for the question two, which one is the at the day? The top one is at the day or the bottom one is at the day? So the top one, yeah, I think most answer A lah. So
A.
yeah, so it's correct actually.
Is it correct? Yeah.
Yeah, yeah,
Okay.
it's correct. The A is at the day. So, but why this diagram correct? Why the compressive stress at top, but the tensile stress at the bottom when it's expand, right? So when at the day, the top part is going to expand. Is and actually not the top part expand, but actually the bottom one is shrinking because of the difference in the temperature, because the top and the bottom will have a difference in the temperature, so the slab is start to shrink. So when the bottom start to shrink, the top to compensate, so it try to bend. So when it start to bend, but the nature of the slab, it have a self weight actually. So when it has a self weight, when it start to the concrete start to bend, but will restrain itself. When it restrain itself, then it will exert the compressive stress at the top. So this is interesting. So at first we also been confused, but actually that's what's actually happening. And then same goes to the bottom one. The bottom one is during at night, the top part will be cooler than compared to the bottom part. Bottom part will be warm compared to the top. Then because of that, it start to shrink at the top, and then but the self weight, you see the both end of the self weight, we start to compensate back, and then we start to push back because of the self weight, and then it start to have a compressive stress at the bottom part. So in this case, that's why when it's meant to have a crack there, then we crack at the at the tensile stress part. So during at night it will crack at the top, but during at the hot time it's going to crack at the bottom. That's what's happening actually. So if you don't trust me, then you can do your own study on this one. So based on this, then the code give us the give a guide lah, how to do the differential temperature effect. So I think you guys are familiar with this diagram when we do the design. I think this one also in the Eurocode, but this one I took from the BS code lah, because this time I used BS code to design the thread slab. So for the thread slab, we use this group 4 to design the temperature difference. So the positive temperature difference and also the reverse temperature difference. But don't forget that we are not looking at the whole deck there. We are looking at the top part only. We cannot use this because it's a full deck is affected by this. So it's not this case, but it's this case. So since we are already interested at the top of the deck, so the H is it should be included with the with the bottom part of the deck. The H is full H. So in our case, our H is just now previously is the height is around like 300 only, 300 something. So so from this, the 300 is easy lah. So meaning that is just only this differential that we are going to assign to our structure. So the top part, I think in this case is just around like 7-degree difference from the top to the bottom of the slab. So what it's going to do? Well, we do a 3D solid element analysis. In this case, I use Step Pro to do the 3D solid element. So I model it full slab. Then we assign the temperature load as per what we calculate just now. Then from there, we after the run the analysis, then we got the results. So this is a result summary come up from the Step Pro. So from here, we check our tensile capacity. We compare against the force that we got from the analysis. So from in this case, so the tensile capacity is still okay. So meaning there is more than the force. So meaning our current reinforcement that we provide is okay. And then other than that two checks, we have other check as well. It's a typical checks. Basically the minimum early thermal crack check. This is to prevent the early thermal crack. I think maybe you already encounter the design in the indoor study. And then another one is the minimum reinforcement. So we have to check all this to ensure that we are still comply to the codes. Okay, so now we finished the design of the bottom slab already. Then we are now designing the derailment wall. This upstand curb is, we call it the derailment. Okay, so in this case, I analyze it using a 3D plate element analysis in the Strat Pro also to get the forces. After that, I use the ASPD. ASPD is a Autodesk structural bridge design to model the sections with a reinforcement to calculate the capacity. So this Autodesk software can do the capacity calculations of the concrete. Then we compare it, then we see our design okay or not. So this is how we calculate. So basically we have the derailment load from the codes. The derailment load code should provide saying that is 100 kilonewton. Yeah, this is based on the UKNX. Derailment is actually, I just give a brief. Derailment is actually when is an accidental loads actually. Is when the track is suddenly derailed from the rail, meaning is dropped from the rail, and then the derailment upstand is try to contain the train from further going sideways. So meaning the train, if it derail, it will still hit the derailment wall, and then we stop there. So we safeguard the surroundings during the accidents. So this is how we calculate. So we with a 100 kilonewton, we apply the ultimate loads factors. Then we assuming the impact width of the wheel is 600. This one we have to find from the locomotive, the car lah, the train car data. Usually we should have that information when we do the track rail design. So in this case, the wheel is 600 mm width. So from there, we distribute it to to make it easy to 100 spacing, 7 nodes. So we got the force already. So from this, I do the 3D plate analysis. So 3D plate analysis, see, similar to just now, but this time is different elements. Previously, I use solid element. In this case, I use plate elements. There's a difference between these two. So to benefit the analysis, so I just use the plate because I want to understand the bending moment only and the shear. That's all. So I use a plate. So I model a full length, and then I apply at the nodes, and then I come up with the results. So the results like this. So in this case, we can see the under ULS, so is a 35 kilonewton meter per meter. This is the maximum bending moment that we got at the bottom of the wall. Okay, and then we do the in the ASBD, the section analysis. It's just the sections, but this section we design it to per meter lah, because we want to compare with the kilonewton per meter just now. Kilonewton meter per meter bending moment. So from here, this is the outcome from the ASBD. We got the internal force. Internal force actually is the capacity, full capacity. This is the force that we apply. Then we have a spare resistance, meaning that is okay. So meaning our capacity is this capacity bending moment per meter. Bending moment kilonewton meter per meter is actually 53.6. This is a capacity. So we do so here summarize it. So the design is okay. Then we check, same check we do for the shear. Shear also we use ASBD to come up with the shear capacity. With the enhance everything, the calculator, and then we found that okay, the shear capacity is within the tolerance. The shear force is still less than the shear capacity. Okay. Yeah, but if you can see, if you see what's happening here, it's like troublesome, right? Why we took such trouble? Why we took this lengthy work to do? For example, just now see we do a 3D plate analysis and step pro everything, quite lengthy to do modeling of the of the elements. Why? Why when if you think about it, we have the point loads there, we have a lever arm, and it is like a simple cantilever. So we have the width of the wheel. I think we can straight away calculate the bending moment. We don't need to do such analysis. It's like a waste of time, right? So why we are doing this? Why we take such trouble? So I'm going to tell you why. So before that, I'm going to show you, sir. See, like what I mentioned just now. So actually from this diagram we can easily calculate, right, the bending moment. For the structure engineer, I think it's very easy to calculate, like we know straight away. We just got this, and then we divide with the width, we got the per meter, and then we times the lever arm. So so this is what I'm doing. Same things. So we divide with the wheel width, then we got the force per meter, actually kilonewton per meter, I forgot to put in. Then the bending moment, we just times the lever arm. Then straight away you got the bending moment, 55.2 kilonewton meter per meter. So why we take such trouble to do the analysis just now? But let's see. Yeah, we see just now. Just now, yeah, we from the SBD, we found out that the capacity, the bending moment capacity is only 35.6, 53.6. So with the our simple analysis, it's failed. But just now the analysis using the Step Pro can pass. Why is that? What is happening here? So yeah, I have a quick quiz. It's a quiz time now. Okay. So which one is correct? The analysis. The first analysis with the Step Pro, or the simple bending moment calculation. Which one is correct? Which one you think? You can answer. I think we have less 10 minutes. Okay, Flo, please answer.
Let's try to answer, guys.
Yeah. If you understand where I'm saying, the first analysis we use all the kind of the step pro to model the elements. Each element we put in the loading, distribute it to nodes, and then run the SBD just to get the bending moment. And then, but when we use a simple direct moment calculation, we found that the direct moment calculation failed, but that analysis is passed. So which one is correct actually? What do you think? Is it A, does the plate analysis is correct, or the B is correct? The with the moment calculation just now, the point loads with times the lever arm, they got the bending moment. Or C is both are correct, or D, both are wrong. So which one you answer? So I open the floor like 30 seconds so that you can answer. Sorry. Okay.
Right, you can try, guys.
Guys, you can just quickly answer. Later I will explain which one is correct. Okay. Looks like most people answer A. Okay. Okay. I give like 10 more seconds. Okay.
Look like from the reply is A.
Hmm. Yeah, but I can see some other answer. Okay, so the correct answer is actually C. Both are correct. Both are not wrong. But yeah, so most of yeah start to answer C. Yeah, correct. Both are correct. It's not wrong at all. But why is that? Okay, so this is the answer. Actually, it's a finite element. This is a finite element method. So finite element method, as explained here, so you can see because of the it's especially with the beam and the solid elements that we use, so is include the shear stiffness. So finite elements is include shear stiffness. That's why the results is tend to give a lower compared to the conventional calculations, especially in the bending moment as a higher deflections, but the bending moment tend to be lower, but the deflection could be higher. This is what as per what the from the Timoshenko beam theory analysis. Timoshenko is actually this. He's a father of the finite elements. You can say. Before that, we used the like a Bernoulli theory to calculate the bending moments, right? But now, when the Timoshenko theory came, so the finite elements is boom to everyone start to use it, and then the software also start booming to use finite elements. So why finite elements give such results? It's because of the shear stiffness. So that's why because if we model it all the small discretized of member for each one as a mesh. So from between this mesh, they share the stiffness. If you understand the finite elements behavior, is that there is distribute evenly between nodes of the stiffness. So the stiffness is tend to be higher compared to the conventional design is is not considering this stiffness, but actually this stiffness is simulates the more actual behavior, real world behavior compared to the one that we calculate. So but whether is it to be reliable? So there's a general rules actually. There's a general rules that finite element will be reliable. First one, for when we do the finite element, we must ensure that the meshing is a good meshing. Meshing is mean that we do the small elements lah. So the small element so I think you can get from the any finite element books that we suggest what kind of the meshing that you should do. Sometimes you can use a quadrilateral or maybe triangular meshing to get the for your analysis. So good meshing. Then the second one is you have the correct boundary conditions. So with these two, then your result of the finite element, inshallah, could give you the correct answer. In this case, I use almost identical dimensions of the small elements, the boundary conditions. So I put the rigidity. So I think in this case, I already meet these two. So the result is reliable. So I think so that's about it. Actually, I wanted to share more. I think we are almost 1 hour already. But I have a few more slides that I'm going to share with you. The what I mentioned just now, the sanity check. What is sanity check actually? The sanity check is that this is that we do when after we do the analysis. What is it about? So sometimes I think I'm not sure whether you already. I think you are already in the third year. I think you're going to in the final year. You're going to have uh your final projects, right? Final project. I think some of you will do numerical analysis. Some of it maybe we do a field study, but some of it will do numerical study. When you do numerical study, you will do more finite element design analysis or structure modeling. So when you do structure modeling, definitely you will come out with problem with error like this. When something like this or all the red color coming out, so you I think most engineer is to find that if what's happening, what I've done wrong. So they're going to start to stress. because of the error. So they always ask, so what went wrong? So you have to know. So this come there's the sanity check. So we have to do the debugging of the structure model when we found the error. So what you're going to do? So, but actually you don't have to worry. So all the modeler always encounter for the not the first time. Until now, also sometimes myself also sometimes when I do modeling, because it's involving a lot of elements, a lot of nodes, so many, especially the is a complex structure. For example, then you are going to use mass quite numbers of elements, and then the loads is so many, the loadings also, the loads combination going more than 40 numbers of load combinations. So sometimes you tendency to have problems to find to get the error or warning. So don't have to worry, but eventually over time when you do a lot of the analysis, then you will start to master this, call it the art of diagnosing the problematic structure model. Or we call it debugging lah, in term of IT terminology, you call debugging lah, but I call it diagnosis, more like doctors lah. So we try to diagnose what is happening with our model, what's went wrong. We went to find. So I'm going to tell you, this is what's the common error that caused the error and the warning. So the first one usually is a unstable model. So how are you going to determine to check whether our model is unstable or not? So first you have to check the restraint. When you find the error, then you check, see whether your model is unstable. So you check your constraint, your restraint, your boundary conditions, and also your supports, whether it's correctly applied at the correct nodes, for example. And then the second one is the disconnected. You could be there's a disconnected elements. And then for this one, you have to check whether sometimes you could be there's a duplicate nodes and beams. So you have to check that one. The third, so this one sometimes the beam will not connect with each other because it's connected to two different nodes. Then the third one is the incorrect material properties. So you have to check properly your property strength. For example, if a steel structure, you have to check whether the yield strength is correct, or if the concrete strength, whether you put the correct strength. Sometimes you put you have to check also the units. Sometimes we put the different units, but actually the model is picking out the different units for Newton per millimeter square, for example, but you put in term of kilonewton. So definitely the property might go wrong. So this is a three core that, based on my experience, that will give you the error in the analysis. So some pro tips here. So usually you just read the error message. The error message will tell you what is happening and then where is it happening. So you read it, don't forget. So I think I just go through faster because we are overrun a bit already. So
can finish it.
Cannot. Okay.
Yes, can.
All right. So we analysis. Once the analysis complete, is it really done? Are you done already? So can we start the element design already after you finish the analysis? Wait, I think you have to hold on a little bit, because are you really confident that your model is correct? So we have to ensure that our model is correct first before we straight away jump to the analysis. So please do check your model first. So how are we going to do the check? So this is another sanity check for the structure. So first, once after you finish, run, then no errors, no warning. For example, if got errors and warning, you have to settle it first. Even warning, although some engineer they settle the errors, but got still like 10 or 12 warnings, you just ignore it. Don't ignore the warning. Sometimes warning also will give you different results. So you have to settle it, the warning, and until you can justify the warning. Why is it? Is it because of the additional load, or maybe the blank load case, for example? Then we give you warning. Then that's okay. As long as you can justify that warning, then you can ignore it. So first thing you have to, after you run the analysis, first you should check the deflection results. And then there's the second one, the support reactions. These two you have to check. So some pro tip here, work out the preliminary support and column load taking prior the modeling. This one that I mentioned it first in the first slide previously during at the flow. Why we need to take the column load taking? Because the column load taking we calculate based on the area method. So that is the most likely correct reactions that we should have get from the model. So when you check the model, you look at the reaction support, it should not shouldn't run further from that value. So if you run, for example, your load taking is like 5,000 kilonewton, but suddenly your analysis is just 2,000 plus, for example. So it's like half is lost. So you have to wonder why. So you have to start dump your model. Then you have to quickly check again everything. Sometimes it might not right there. The deflection is even more. Deflection is will give you everything. At the first glance, you already know the deflection whether correct or wrong. To do this, you have to know well you have to very well versed in term of structure analysis. You have to know before you run. You already know what's the deflection that you should look at. For example, if the multiple span, then you have to see where's the sagging should have, where should not, where they should have very high hogging, for example, in terms of deflections. So if your deflection something went wrong, something not right with the analysis, don't bother to look at the results already. You have to diagnose your analysis first, your modeling first. So that is a part of some of it. So the another one is whether you are an engineer or the button pusher. So this is just some of the some of the nasihat. So actually the software is a powerful slave, but it's a poor master. So it should have a master, and the master is you. You're the modeler, the engineer is the master to the software. You have to remember this. You don't simply blindly take the results from the software. It's powerful, but it's not a master. It could be wrong. It give you whatever. You put rubbish, you come out rubbish definitely. So you have to be careful there. So the pro tip is that so if you cannot estimate what's the result, for example, the deflection or maybe the bending moment diagram, so then you cannot trust the computer already. So meaning you have to make sure that yourself you know what you are doing. For example, you do a frame analysis in the model, you should know what's the bending moment is going to have. So that's one of some of the tips. Then the final two, I think we almost finished there. So this is some of the rule of thumb in doing the analysis. So this is the deflections. So the rule number one that I mentioned just now, the deflection. The deflection is the truth. The deflection will show you everything. So for example, you look at the right hand side. When you saw something like this, definitely something not right here. It could be because of the compressive the spring here maybe not correct. Yeah, it could be. So we have to look at the model again. So the deflections is the key. So again for this one. But this one actually, well, although it looks like very weird, why suddenly decide have more, but actually it's just almost 7 mm is very small actually. But it could be wrong also because the behavior is quite weird. So we have to always doubtful with our model. not to not saying that you don't have confidence in your model, but you have to feel the confidence first. You say, oh, okay, this is a correct ID. So okay, then I can proceed with the analysis. I can proceed with the element design. So yeah, so this is what I mentioned just now. So why the deflection is because it's revealing the modeling error. So first you just look at the shape, you already know. Don't need to even look at the numbers lah. Numbers can be a second thing. The first thing is the shape. So I think this is the last part of the yeah. This is the some of the rule of thumb on the doing the design. So we estimating the depth before even the computer does. So normally for standard beam, for example, you know the length, for example 6. So for if a continuous, yeah, you just divide by 20, then you know the depth, the average, maybe the pre-estimate depth of the beam that you are going to use. For slab is L over 300 or to L over 35, and for cantilever usually L over 8. So based on this, for example, if you have a 3 meter span cantilever beam span, so you can calculate. Oh, maybe I need this depth. So this is some of the rule of thumb that you should use lah to doesn't it say that I'm not saying that it's a must, but this is usually is almost correct only. So is fast is can ease your work later on lah. So you don't have to change so much. The failure also not very big, for example. And even you can pre-calculate your estimation of the cost also. So you should have some confidence when you have this kind of rule of thumbs. And then for bridge engineer, usually we use predetermine the span. We have to determine what the span length. Usually the end span, it should be 0.6 length from the mid span. Why? Because of the anything shorter than that for the end span is going to cause the uplift of the bearing. So we don't want that. So in this case, the 0.6 is the most ideal one. The longer than that is not economical already. So that's some of the rule of thumb that I'm going to share. Oh, sorry, got last one. So this is like a typical detailing rules lah. So this is also the rule of thumb. Usually, what is like you just look at your beams. For example, you got a beam is greater than 600. Usually, you should have a side face bar. So when you look at the drawing, you have a 750 millimeter depth beams, but don't provide the side face bar. There's something not right lah. Meaning you have to query on that one. Then usually it should have a side face bar as per the codes. Even more deeper than that is even need more side face bar. Then the another one, the rule of thumb is for the column reinforcement. Column reinforcement spacing. Usually you should not exceed the main reinforcement should not exceed 150 millimeters. So from here you can roughly know what's the rebar percentage already lah. You can predetermine. You don't provide like very big columns but very few reinforcement until more than 120 millimeter spacing. Yeah, that's some of the rule of thumb that I'm going to share. I think I end my session already. So maybe you can quickly open the floor for the question Q&A. I'm sorry that I overrun like around 11 minutes.
No worries. Thank you very much, Azizul, for the very insightful about really moving from theory to reality from your experience. Okay, guys, now we are open for Q&A session. So you can raise your hand and directly can ask, please. Any question from the floor? Yeah, please grab this time to ask the very experienced persons. If you wish to be a professional engineer in infrastructure like Azizul. Yes, any question? Oh, sure, you have a lot of questions, but you want to ask. Please do ask.
I understand next week they're going to have a break already, right?
Yeah. All right. Okay. Maybe I can ask. I just wondering because you have experience of do calculation and redesign. Have you encountered a design that had to be changed significantly during the construction, and why that happened?
During constructions, you
Yeah,
mean
suddenly change the design.
after the design is done, we issue out the construction drawings, but they still have the construction issue. I think usually it's not going to change quite a lot lah.
Mm-hmm.
Unless there's something not right is happening in between lah.
Mm-hmm.
Sometimes lacking of the communications, it could happen.
Mm-hmm.
Yeah.
Oh.
But well, with a good project management teams, usually is not so much. Usually the changes may be due to the sudden constraint at site, for example. Then you have to do no choice to do the changes.
Mm-hmm.
Yeah. Before we issue use for consultant, I'm speaking in a perspective of consultant because I
Mm-hmm.
always been in consultant, never been in other parts, other parties lah. So in a consultant, usually before we issue out the construction drawings, we have to carefully, we already go through a lot of things. For example, we go through with our PE, our PEPC, our endorser,
Mm-hmm.
engineer. He's the most experienced in the firm lah usually. So he know all the rule of thumb, everything. So when he sees, already know something not right. Usually lah. So we go through with him, and then not only that, we go through sometimes client also have their own engineers, and
Mm-hmm.
also already review the drawings, everything should be in place. And in Malaysia, usually the large project, for example, we need to have a checker. We call
Mm-hmm.
it ICE, independent checker. So usually for JKR projects, always require independent checker submission. So independent checker have to do their own diligence to check whether the design is at par or not. So usually the changes is not because of the negligence, but it could happen sometime, maybe because of the misinformations, or
Mm-hmm.
maybe the poor, as I mentioned just now, poor communications between the, or maybe the poor study at site. For example, SI
Mm-hmm.
results,
Yeah.
the sub consultant do poorly the test, and then it come up with a different result compared to the actual one. So sometimes that's could happen. Yeah.
All right. Thank you very much. Any question, guys, from you? Maybe we can take one or two question, please. Tak nak tanya ke? Ada orang experience kat sini.
Well, I think dia orang pun dah okay kot. I think
Uh,
I hope
so maybe since this student maybe in 1 year's time they be graduated, so maybe you can give them a guide or suggestion what they should do to start preparing for professional engineer, and what route they're going to follow, or something suggestion or thought for them for young engineer.
okay. You're talking about the professional engineer from BEM lah, right?
Yeah,
Okay. So for
maybe
the
give them
yeah,
advice for them. Yes.
pursuing professional is actually is self, we call it apa, macam it's a personal preference. Some, I think a lot of my friends don't bother to get the professional. It just that based on engineer, and also sometimes our bosses pursue it to go for the professional, for example. So it depends. But if you keen to, is good, because of what? Because you can like self evaluate yourself. So in preparing to answer that, the in preparing one, usually the minimum requirement, I think last time is like 2 years. I think this time I think maybe 3 years. I'm not mistaken. The latest one I forgot already. So during that time, you learn, you gather all your experience as much as possible. So meaning that you really learn. Then don't forget to save all your works. You have to, previous engineer that they suggest me to do some logs books, but I didn't do that. But what I did is I saved most of my previous jobs lah. So the drawings, your calculations, you save it, or take photos when you have a chance to go to site, for example. Those later on you will be used to for your PE submissions reports. So it's beneficial you very much. So during the period, for example, the 3 years, the first 3 years, you gather as much as you can.
Yeah. Thank you very much. So listen that guys. So please remember save everything. Yeah.
Yeah.
As what said by IR, and since you have a mobile phone and can take sort of picture, please keep the data for you for yourself if you plan for to be PEPC in near future. All right,
Yeah.
I think that's no more question from students. So thank you very much, Azizul Afandi, for very
Okay.
insightful and informative
All
about
right.
your experience.
So here
That's
I share my cards here. You can take a photo or what, can save it. So in case you have questions, you need to some consultations, so you can ask me, you can text me, or you can email me or WhatsApp. I don't mind.
yes, yes, good.
Or maybe once you graduated, you want to maybe to drop a CV to me also.
Yes,
I
that's good.
can. Yeah, of course. We for example in AIS also we are really try to yeah, we are now is like looking for young engineers. We are keen to train the young engineers. So please,
Yeah,
yeah, you can take save my at least my emails. Yeah.
yeah. Please save, guys. That's good opportunity for you guys from senior bridge engineer from this company. So you can try and he can be mentor for you for your journey. All right, I think that's all for tonight. Thank you very much,
All
Azir
right.
Effendi, for your
Thank you so much.
very
All right. Yeah.
time. Finally, you can make it. I
Okay.
think that's all for tonight. Thank you very much. Assalamualaikum and have a good evening. And don't forget to study
Waalaikumsalam.
for final exam. Assalamualaikum. Have a good evening.
Okay. Salam.
Terima kasih.
Baik, baik. Terima kasih, Doktor.